Good morning, everyone. I'm Ryder Safgelia, and I'd like to welcome you to this second of the GeoEnviroPro talks this fall. Today, Guy is going to speak about the quality of chemical data, and his alternate title is "Why Bother with All This Stuff? It never seems to make a difference." Yeah, but first a word about the format. For those of you who did not attend previously. The webinar presentation itself will go for about 20 minutes, and then we'll have 10 minutes for questions, and if there's lots of questions, we'll stay a bit longer. If you have questions during the talk, send it to me using the question button. I'll be the host, and I will monitor the questions as they come in, and I may reply on the fly or hold the questions for the question periods. So over to you, Guy.
Okay, thanks very much, Ryder. So as Ryder mentioned, I'm going to give a talk today about the quality of chemical data, or why bother with all this QA/QC stuff, because it never seems to make a difference. And what do I mean by that? Well, here's some observations I'm going to share with you, and I dare say many of you would agree with this. But if you don't, please use the question button and send in your comments. So the first point, we all know there's a lot of slop in our soil and groundwater chemistry data. What I mean by slop? Well, concentrations vary from actual values. Our duplicates are rarely the same. And by the time we're done our investigation, we know there's some uncertainty in our data set. That's a given. We also know that the chemistry data for soil is much more variable than that for groundwater. And that's a pretty common understanding because of the heterogeneity in our soil samples. But now look at this. If we look, we rarely find a problem with the final laboratory chemistry reports in terms of their QA/QC. I know there's been, some issues in the past and whatnot, but I mean, the labs we use, the certified, CALA certified labs, I mean, it's their business to give you quality data. And we almost always accept their data for comparing against our standards. So another observation, for soil duplicates, these are what we do in the field, and this is kind of the focus of today's talk. We almost always find one or more substances in our soil dupes that exceed our RPD targets. And RPD, as you see, is a relative percent difference. I mean, most of the time we're pretty good, but soil always has a problem. And do we care about it? Well, we almost always attribute soil chemistry variance to what we call within jar or within sample heterogeneity. And that's, in a sense, that's why we justify not worrying about it. And then in our final QA/QC reports, just about every report I've read, it almost always has some boilerplate, meaning we went through all this exercise, everything's to meet our quality assurance targets. Let's get on with the reporting. Everything's good. Just about always that happens. So why are we spending all this time on this QA/QC stuff? Are we just wasting money? So here's some questions. When does that slop in the data become relevant to your site assessment or investigation? Can that slop actually affect my conclusions or my recommendations when I'm writing up a report? Like, when do we really have to worry about this? And should I be concerned? Well, I got to start off with this exercise, and I'm sure many of you have seen this before. I'm going to give you 4 scenarios, and this is intended to get across the issue of precision versus accuracy. And here, this scenario 1, if I told you if I asked you, does this scattering of the data points, does this represent high accuracy or low accuracy, or high precision or low precision? You're welcome to type in your answer in the question button there, but I'm going to just tell you right now, this is an example of high slop. If our actual true value is the red circle here, we see that none of the points actually hit the mark. And there's quite a bit of scatter. That is imprecise. But then the question might be, is this accurate? And I dare say, if you were to measure the distance from the points to the center of this bullseye target and then take the mean, you'd probably land right in the middle of our target. So in a sense, this could be considered accurate, perhaps even highly accurate, if you have enough data points and run the stats on it. And that's something we're going to talk about too. In this scenario number 2, now we have something that's, I'll call it highly precise and highly accurate. It's very close to the bullseye if most of the points are hitting the target, and there's not that much scatter in the data. So it's pretty high precision. Now here's something else we might talk about. What happens when we use some field techniques or the laboratory's instruments aren't quite tuned, and we put some bias in our results? So we're actually getting a good clustering of the data, but we're not hitting the target. We're going to talk about that a bit today too. And then finally, scenario 4, imprecise and off target. This is time to throw your data out. And I've rarely seen that happen in an environmental consulting report, because usually we're not that bad. But what leads to high quality data? Well, first, conceptual site model. And you maybe have seen me talk about this on prior occasions and on other courses and whatnot, but it's it's the fundamental tool we use as environmental consultants to try and understand what's happening at a site. In terms of getting good quality data, we use the conceptual model to help us select, I'll call them well-chosen sampling locations. And we target chemical analysis so that it includes the contaminants of concern and maybe some other indicator parameters to help us better understand what's happening at our site. We also use acceptable field methods. Hopefully we're using ones that are that lead to high accurate data, and we did in the past and we will in the future, so we can have comparable data from one year to the next. We also use data quality control measures, proper data validation and interpretation. Uncertainty in data is described and quantified. And then lastly, and this is one I threw in recently, but once we've got all this, we've done the right things, we've got our data quality control data back, we need to look at that data and reassess our main database to see if there's anything that would affect our decision making. Have we got a contaminated site or not? Have we cleaned up a site or not? Have we characterized that stockpile properly? And if reassessment says we have too much slop on our data, for example, we need to take actions to reduce that uncertainty. Again, a couple of, I'll call these pablum slides, but it's important to consider this when we're talking about the quality of data. There's certain sources of slop in our data where we have reducible error. These are things we can fix. Measurement errors, we pick the right analytical methods as a laboratory, or accuracy decreases. If we recognize that accuracy decreases near method detection limit, we have control over that, and that we can try and use methods or have the lab use methods that reduce detection limit and therefore increase accuracy. We also know that when we're in the field, we have sampling errors, meaning that we might not get our sample from exactly the right spot, or we might be cross-contaminating with dirty hands or something, poor refrigeration, or our field procedures weren't exactly followed correctly. So we can improve on those things. But there's also sources of irreducible error. These are things we don't have control over, and so we have to compensate by, we'll call it usually oversampling. And natural variability is the biggest issue here. A lot of the imprecision we're going to be talking about comes from the variability we have in space and in time. So in space, meaning with where we're taking our sample in a plume or in a soil area, or with respect to groundwater, usually it's the time of day, or soil vapor, time of day or season. And here's another thing I wanted to run by you. This little acronym, I find it very useful, actually, the PARCC acronym. Many of you have hopefully seen this before too, but this is a reminder about each of these elements of quality assurance that we should be discussing when we pull together the data for a site investigation. And it should actually find its way into report. So the first is precision. These are measurements that are repeatable. And we're going to talk a bit about this in a few minutes. And this is where our duplicate sampling comes in. Then there's accuracy. These are the measured values that we're getting close to the true values. That's usually a function of a proper lab that helps us ensure proper accuracy. Representative, the sample should represent what's the condition being measured. Here I've made a note, and again, this is mainly to do with soil, but you want to have enough data so that you not only have the highest concentration at your site, you also want to have enough data to know the median and the mean, for example, maybe percentiles, so that you can quantitatively compare your data from a, let's call it a population of soil samples against the standard. And you're not just taking a one-off high number and getting everybody to overreact. But we can talk about that later too. Complete for quality assurance. This is a pretty simple one. Did you actually do everything you said you were going to do? Did you get all the samples from the right places? And then comparable, can the data be compared with other data sets or other data at the same time collected by different persons, for example? Were the same or similar procedures used so that you can compare them or not? Or was there bias introduced? And as I mentioned, these PARCC things, these are what I look for when I'm reading the QA/QC section in an environmental site assessment report. I mean, I'd like to know that everything that was done, that was required to be done, got done, or most of it. And I like to know that the the data are accurate and there's some comment on precision. All these things should be touched on as part of a QA/QC section. It really helps give confidence to the reviewer, for example, that you've hit on all the right bases. I'm going to just go through, I'm going to leave precision for the end here. I'm going to go through these other points just to touch on them so you're familiar with how these terms are met in the QA/QC program. So for accuracy, that's the degree of agreement between measured and known concentrations. This is something the laboratory handles. They have reference standards. Different laboratories get reference standards, and they, I guess it's sort of, they're members of programs where they run these samples and send them to independent organizations that rank the accuracy of the different labs. So, and it helps them maintain high quality and high accuracy. The labs will also run, in addition to reference standards, they'll run matrix spikes, usually on your samples, where they actually take a sample from your site, which may have some contamination in. They spike it with the same contaminant, so you end up with a higher level. Then they analyze it and see if they get it all back. Another thing about accuracy is sometimes it's comparable to the term bias. Bias is the tendency of multiple data points in a data set to be inaccurate in a systematic manner. So here we've got an example of a biased data set. Everything's quite precise, but it missed the mark. This is, for example, might be in the field example, somebody that's using polyethylene tubing to sample low-level PAHs from groundwater, and the polyethylene absorbing all the pHs, so you're biasing the results low. It may also be that the laboratory, they're tuned to concentration data set that might be somewhat different from another laboratory. So laboratories can introduce bias, and there's an acceptable level of bias that we have among laboratories. But I do like to note that the times, and I hope I don't get in trouble with the labs here, but the times I've sent same data over to different laboratories, same samples to different laboratories as duplicates, you end up with mean concentrations that aren't necessarily the same. Sometimes they might be off by a few percent. Sometimes, I don't know if you want to call it significant, 5 or 10% difference may not seem like a lot to laboratories, but if you're dealing with soil samples that are right on and around a critical point, such as a standard, then this can become a big deal. I wish we had the budgets to be checking on labs and comparing them so we have comfort in the accuracy of our data, but we don't seem to spend a lot of time on that. This laboratory spike thing I talked about, this is where you'll see in the laboratory reports a percent recovery, where your laboratory takes a known spike concentration, they add it to another sample. So here we've got a spike of 0.75 microgram per liter added to a sample that already has 0.13 microgram per liter of this unknown chemical. And so the spike, they spike it and then they analyze it. In this case, the analysis came back with 0.80 microgram per liter. If you add up 0.75, 0.13, they should have got 0.88, but they only got 0.80. So this little calculation allows you to determine the percent recoverable. In this case, 89% recoverable. Is this acceptable? Well, it usually is, but you should realize that the labs are not, some parameters they do very well. generating 100% recoverability plus or minus. But when it comes to soil and when it comes to some of the more highly absorbed contaminants, let's say, for example, benzoate-pyrene, it's not uncommon to get a percent recoverable of 50 or 60%. And it's not uncommon for the lab to say that's pretty normal. What is uncommon is for the poor risk assessor to not be aware that the data that they may be using in the risk assessment may be biased low because 30 or 40 or 50% of the mass of this carcinogen is absorbed onto soil and may not actually be reported in the analysis. So moving on then, measuring data quality and representativeness. This is the degree to which samples reflect soil or groundwater conditions from which they're obtained. So to get representative samples, we usually have a professional, a qualified person using acceptable approaches. And this, for example, might mean using professional judgment about where to get samples. But something we need to keep in mind, and this is the subject of another webinar we'll be presenting later on. I'm sure maybe Ryder will do that when he talks about soil. But we can bias our results high by purposefully picking samples that likely to have the maximum concentration. This happens all the time in our work when we're drilling boreholes, for example, and taking soil samples and screening them so that we can select them for chemical analysis. There's nothing wrong with taking the highest concentrations in a borehole, but we have to remember that we are using professional judgment and it's not representative of conditions along the entire soil column. And that might be the same for looking at a surface area where you're trying to characterize metal concentrations. You don't just want to know the highest, you want to know what's happening in the whole population of soil. So with that note, we also sample in accordance with professional practice and regulatory requirements. And by that, we also hand in hand tend to, or we should be using standard operating procedures that give some consistency, and they've been reviewed and accepted by others as providing reliable data sets. This term comparability, this is the use of consistent sampling and analysis procedures. So comparable or consistent techniques is a key to getting good quality data. Then finally, for completeness, the last C in our PARCC acronym, this is just doing what you said you'd do. So the percent completed is a simple calculation. How much did you actually do versus what was planned? Now we get on to this precision thing. This is the real slop in the data, in my view, that we should really spend some time on. So this is the degree of agreement between multiple measurements of the same parameter. So here we've got a duplicate, concentration 1, concentration 2. The RPD I mentioned, the relative percent difference, is just the absolute difference in concentration divided by the average of the concentrations times 100. So let's see, what does that mean? Well, it usually comes out as a percent. And here's some typical, we'll call them control limits for somebody's analytical program, where they set the acceptable RPDs for groundwater and for soil. And you can see these are buzzing around 10 to 30% for groundwater and 10 to 50% for soil. And I made a note here. For soil, the RPD limits are almost always greater than those for groundwater. And why is that? Well, it's because of the heterogeneity. So what's with the soil? Here we've got somebody that's logging some soil cores coming out of the ground here. You'll notice there's a bit of heterogeneity in there, some fracturing. Here's on the right side, this is a pile of silty material at a smelter site that was high in copper. We've got some malachite oxidation, or copper oxidation with malachite. And here's just a blown up sample of a sand, recognizing that when you look at our soil material, we know it's heterogeneous at small, medium, and large scales. So how does this heterogeneity in soil cause data variability? Well, we can get variability within the jar, within the sample that we've talked about. We can get it at a local scale, and this is meant to be an example in a plan view. Supposing you want to get a sample of a single population of soil over a meter, you might take a few aliquots and mix them and put them in a jar to get a representative sample over that larger area to try and smooth out some of that scale at the scale of centimeters. And then we have large scale variability. So here we've got somebody sampling over a larger area where we actually may have some not necessarily single populations of contamination, But even within the single population, there could be quite a bit of variability or heterogeneity. So these have to be considered. But the precision, when we take duplicates, we're mainly focused on, we'll call it within jar, although we don't get true duplicates with soil or groundwater for that matter, unless we mix them before we put them in the jar. We rarely do that because you'll lose volatiles, for example. So we fill up the jars usually consecutively, so they're not true duplicates. You need to remember that. In this example, one jar for an arsenic came back with 16.5 microgram per gram. The other sample, the duplicate, came back with 19. So to calculate your RPD, we go through a little analysis. In this case, we have an RPD of 14%. Is this acceptable? And certainly if we use those limits before, 30% for metals, 14% is acceptable. But what does this really mean? And what happens if we had a different duplicate set where we had 12.2 and 19 microgram per kilogram per gram? In this case, you crank through the RPDs and we get 44%. Is this acceptable? And I'd say, nope, this is over top of our 30%. So what do we say in our reports? Well, we say in our reports, that's too bad. It's within jar variability. But because the samples are below our standard of 20 microgram per gram, I think we're okay. So you write it up, Bob's your uncle, and away you go. And is that the right way to be looking at this data? So what I want to draw your attention to is this bullseye thing again. When we take duplicates, supposing I had a sample and I took 12 duplicates and analyzed them all. So that's what we're looking at in this bullseye here. We've got, I think it's about a dozen points here, all from the same sample. There is a mean here, but in order to get that mean, we need at least, in this case, a dozen samples to capture that variance so we know what the actual number is. So we rarely take 12 duplicates to try and get our real answer. We take 2 samples. So supposing in this example here, if one of my duplicates was way low and another one was way high, if I take the difference, I end up with a high RPD. But look, when we take duplicates, we don't know if that duplicate is representing this guy and this guy, or this guy and this guy, or these two close together here. If our duplicates just happen to be similar to each other, even though we have very poor precision, we won't know it from one duplicate. If you know what I'm saying, this duplicate thing, it's an indicator, but it of itself, it isn't telling us a whole pile. If you really want to understand the slop in your data, you need to have more analysis of that single sample, and we are rarely going to do that. What we sometimes do is we pool our data sets, and maybe Ryder can comment on this when I'm done talking, but if we have the same population of soil, we can pool it and get an understanding of the variability by looking at multiple samples. And this is again now assuming we have a simple singular population, therefore a single target. But really, most contaminated sites, is that the case? Maybe if you have homogeneous fill where it's been mixed up and you can actually treat it as a population with variance in space. But most of the times we're dealing with concentrations that vary over space. So they're going from high to low concentration areas, for example. You're not dealing with a single population with that meaning a single value of the mean when you have spatial changes. So we have to think then, what are these RPDs telling us and what are they not telling us in terms of the slop in our data, and does it matter? So let's take a look at an example here, and I picked this one for arsenic. I threw on a couple pictures of smelters that are known to have arsenic contamination in the environs, one from the Northwest Territories of Canada and one from Namibia, both with these nice little issues. So is the site contaminated? You've just embarked on a program over an area where you think you got maybe some spatial variability, but you're not sure. And you've taken some samples, and here's some data, some shallow soil data. Here we'll use the Canadian standard, or the BC standard rather, of 20 microgram per gram for arsenic in soil is acceptable. We've got a series of 7 samples. Not a bad data set, but maybe from statistical point of view, that's not great. We've got 1 duplicate. Our duplicate is the same as we showed before, 16.5 and 19, so we've got an RPD of 14%. Hey, everything's fine. When you look at the data though, is the site contaminated? This is the question you're trying to answer. You've got a couple samples over the standard, a couple near the standard, and if you were to, I don't know if you were able to take the mean of this data, I dare say you might end up with something just under the standard. But the question is it contaminated? When you recognize the amount of slop in the data, even acceptable slop by this duplicate, are we over or under? And what does it really mean? And that's something I do want to get some comment from you, Ryder, on about things we can do when we have to make decisions around this data, and we don't really have a good handle on the variance in the data to make these decisions. I just think it's becoming an issue. So to wrap up, before you answer, Ryder, I'm just going to wrap up. It's just got another couple slides here, but for a successful project, QA/QC, you should think about your data quality objectives before you start the program. Like, what are your RPD limits that you're going to be using? So there's no surprises. You don't need to fudge things at the end. You need to have picked your proper sampling procedures and all that kind of stuff. So use the acronym PARCC and think about it and make sure you've thought about all those issues. Implement the plan and assess on an ongoing basis to make sure you're meeting your objectives. But think about the implications of your QA/QC results on your conclusions and recommendations. It's not just a matter of comparing numbers to standards. You're done. We have to think about this data, particularly when for some parameters where we're near what we'll call a decision-making unit, such as a standard. I mean, if we've got RPDs showing up at 20 or 30% in just a couple duplicates, it doesn't just mean that only applies to the duplicate. It means we've got a lot of slop in our data for that parameter. And we've got a very, very limited data set. But if it does apply to the whole parameter, then you have to go back and look at all your data and think about the implications of having plus or minus 30% in your concentrations. What does that do to your interpretation of what's happening at this site? What can we do? Here it says take corrective action, but for precision, Ryder, maybe I'll put this to you. What do you think we can do to if we're not comfortable with the precision of our data, or we don't think our two duplicates that we took that all came back ND, it's kind of useless data. What do we do? What do we do? What should we be doing? Any ideas?
Yeah, I think on the RPD, the way to look at it is if you have RPD that exceeds the recommended acceptable range, which is typically 20 to 30%, that's really a flag for you to look deeper, to understand why. Why do we have more variability than we would expect, or what's typically accepted? And one thing, the first thing you should do is check all the numbers in the tables, or check what the lab sent you, so there hasn't been any mistakes in transferring data. The second thing you do, actually, and this is important, is to inspect the sample. The soil sample should be stored. The labs will typically store them for 6 months. You would ask to retrieve that sample. You would actually study it, perhaps go to the lab if possible, and the other thing you would do, you might actually have the sample retested. So this slide is good. The bullseye picture on the side, Guy mentioned that typically we only do 2, but really we should be doing 12 duplicates.
Are you advocating that too, Ryder?
And not for every sample, but if you have, say you have an RPD of 50% and you have checked the tables and the transcription of the data from the lab and you don't see any problems there, and you look at the jar and you don't see readily why it should be 50, why the RPD should be so high, then you may have the lab run 2 more tests on the same jar. So then you'll have 3 replicates and the original sample. So actually 4. And now you are better able to answer the question, is this just part of the in-jar variability, the scatter that you see in this bullseye? So so that's how I treat the QA/QC. It's a warning signal that something could be wrong, but it's not necessarily wrong. It may just be part of the intrinsic variability of the sample.
That's interesting, because I don't disagree with you, and I think those are good suggestions or recommendations. Having said that, though, I rarely see consultants doing that. What I see is, you know, for example, a program that might have 50 or 60 soil samples. If they're running 10% dupes, then they'd have 5 or 6 dupes. And let's use the arsenic example. So of the arsenic dupes, let's suppose 1 or 2 of them exceeded the RPD of 30%, but the others didn't, and the consultant just concludes, oh, well, you know, within jar variability, let's move on. That's what I read, and you've probably read that too.
Yes,
But
and
how much checking did they
I think there
actually
is
do?
distinction between there is a distinction between being marginally outside the range, say 30%. Say you're at 32% RPD, then you may pool the data. You may look, say you did, for argument's sake, this was a large site, a mine site. You did 100 samples, so you have at least 10 dupes, maybe 15 dupes. So now you may look at the other dupes, and if they all fall within 30%, then you may say, oh, it looks like this one sample is a bit of an outlier, but overall the data quality seems good. It's different, for example, if you have an RPD that's much higher, where you have a much bigger difference between the original sample and the duplicate. That's when you go back to the jar and look at the soil. And one of the pictures you showed there with examples of variability, and the one that had the red and black spots in them.
If I can find that one.
I have had a sample like that had high pH, that one there, and it had high PAH readings in the duplicate. The original sample was low in PAHs, and the duplicate was much higher. And what we discovered there, when we went and inspected the jar, it was actually asphalt particles in the sand and gravel. So then we now understood why it was variable, and we're able to deal with it. So I think that's
well, how you deal with
it.
How you deal with it is probably a subject of a different webinar here, but that's the same in this example above the soil, where if you took a sample of this other sample, this this stuff with the green malachite showing up, you might get a crumb of that and blow the doors off your copper concentration, and the other duplicate might be low. So it gives you an idea what you're actually dealing with, and you make decisions accordingly.
That's quite common. And that's quite common. That happens also, you know, lead from sandblasting, you know, paint flakes with lead. You often see that as well. You see, you have small particles or in the soil sample that have high concentrations. So what it comes down to, I think, and it's something you mentioned early in the presentation, Guy, it comes back to the conceptual site model. So when you get this information, you ask the question, why? Why are we seeing this difference? You look deeper, you go back and reanalyze or re-inspect your soil samples, and then you may go back to conceptual site model and say, why does this happen? Well, perhaps it's because you have these paint flakes that's scattered around the site from sandblasting of buildings or structures that have been painted, stripped for paint and then repainted. And then you would then perhaps come up with a different or an additional analysis scheme where you look more at leachability because you're concerned about pathways. And so that's getting into interpretation of the data beyond the QA/QC.
But Ryder, just I imagine our time must be getting close to wrapping up. I haven't been checking here, but this example again with the bullseye though, what about the case where you have poor precision, but your duplicates happen to come out very similar, so you actually now you don't have a clue that you've got lousy data?
No.
That must happen. That must happen, as you know.
Yeah, but that's what you brought that up in terms of pooling the data. So that's, again, if you have, it always helps when you have a site with more data. So if you have, I would say, more than 10 duplicates for a site where you're investigating a particular soil unit, then you have enough data, and now you can look at the other duplicates and see what pattern you see in terms of the relative percent difference.
So here's the question I have, though. When you pool the data, but you only have 2 or 3 duplicates in your program, that's not a lot of pooling going on.
No. So we can't really. No, that's where I think professional judgment and the conceptual site model comes back. It's kind of understanding your site and understanding what you expect, and there's more judgment required. And perhaps if you get results that look, questionable, or then go back and take more samples. I mean,
Right.
that happens. You have to go back and say, well, we didn't collect enough samples to really answer the question we were wanting to answer. So we got to go back and collect a few more samples.
Oh, I don't doubt that's what should be happening. But again, I don't see that many reports that is happening. That's in part why I thought this was an important webinar to put on. I think people need to think a bit more about this data and make some better decisions when they do need to get more data to get a handle on the kind of slop, particularly when it's relevant, because it's around you're dealing with a site where you may have some areas that are over applicable standards. So anyways, I think it's time to wrap up here, Ryder. Did you want to say something about what we're doing in 2018, 2019?
I will do that. But before doing that, we'd be interested in hearing from you. We always send out a survey after the webinar. Perhaps you want to jot down a few lines about your experience with PARCC at your sites, and we'll find an opportunity to bring that up later. We plan to have a field school webinar series where we deal with soil sampling and groundwater sampling and so on. Yeah, so what's happening in this fall and winter term, we have our regular GeoEnviro Pro Talks every Wednesday until mid-December, and they, as you know, they start at 10 on the Pacific Standard Time and go for 20 minutes plus 10 minutes questions. We also plan a few 1-hour professional training webinars, and the topics we're looking at is PFAS, site investigation strategies, technical report writing, some selecting effective remediation remedies. We'll present on some case studies, and the last one there is the site investigation I mentioned on sampling approaches and methods, where we want to have sort of simulate a field school on how to plan and sample soil, groundwater, biota, and sediment. We also are going to have some face-to-face event in Vancouver. The first one is going to be November 1st, and that's a contaminated site regulation update. So that's quite specific to BC. We will also, we're going to try to do a live broadcast from that event as well as a recording. So those who cannot attend in person may be able to either log in during the event or watch the recording afterwards. And the same is true for the risk solution. We held that last year in April. It was very successful. And that's where we deal with risk assessment, successful application of risk assessments, and how sites were able to remediate and risk manage sites successfully. And last, I want to just mention that we have a number of recorded webinars available on you can go to our website, and that'll provide a link to Thinkific, where the recorded webinars are stored. And we have a fundamental series that deals with sort of the fundamentals of site characterization of soil, groundwater, and soil vapor. We also have human health and ecological health risk assessment. We have webinars on dry cleaners and on
Yeah, I know.
remediation.
That's mine.
Statistics, that's yours, yes.
Yes, I'd encourage you all to take that one.
Yeah, we also have on creosote sites, and that's what I did. You know, an overview of sites with creosote contamination, as well as some case studies on creosote contaminated sites. So maybe the next slide, Guy.
Yeah. I think. Well, we know what these talks are. I'm going to go to the next slide, actually.
Next one. Yeah. So this is something we have been promoting over the last few months, and that is for you to sign up as a member, or your company can sign up for the whole team. We find that useful. We provide unlimited access to all the GeoEnviro Pro talks, recordings, and discounts on events, free PDF downloads, and professional development certificates. The fees varies from $10 a month up to $50 a month, $100 a month, depending on whether it's individual or businesses. And by signing up, you have access to various training materials, and you support us developing more training materials. So thank you, and over to you, Guy.
Yeah, no, thanks a lot, Ryder, for that overview of what we're up to here, and appreciate all you for listening through on my talk on QA/QC. I look forward to any questions or comments you have. Shoot them on the email or send them in, and we'll do our best to answer them. So with that, I'd like to end this webinar. Thanks very much for joining us. Bye-bye.
Okay. Thank you.